Welcome back to the deep dive. Today we're taking a really close look at a preprint that's making some waves. It challenges some fundamental ideas about representing images, in latent space.
That's right. And this is aimed squarely at you, our audience experts who live and breathe machine learning, data science, and the underlying math.
We're focusing on this paper. An image is worth 32 tokens for reconstruction and generation. It introduces something called TiTok, that's TiTokk, a transformer-based, one-dimensional tokenizer.
And our goal here isn't just a quick summary. We're aiming for a meticulous, really comprehensive, and purely factual deep dive. We'll stick strictly to the paper's architecture, its methods, and the experimental results presented. No outside speculation, just what the authors reported.
Okay, and we have to start with the headline finding because it's pretty striking. The scale of compression they're talking about, it's significant.
It really is. TiTok manages to represent a standard 256 by 256 RGB image using just 32 discrete tokens.
Right, 32 tokens. And just for context, think about existing methods like VQGAN, which are, often the workhorse here. They typically need 256 tokens for that resolution.
Or sometimes even 124 tokens if you're pushing to higher resolutions and want decent quality. So 32 versus 256 or 2024. It's a massive difference.
That compression ratio, potentially up to 64 times fewer tokens, that's the core technical bit. But what does it mean practically?
Well, the impact is really about efficiency. TiTok doesn't just claim competitive performance, and in some cases, they actually show superior quality on certain benchmarks. It also offers a huge computational advantage.
Especially in generation, right?
Exactly. When generating images, particularly at higher resolutions, like 512 by 512, they demonstrate speeds up to 410 times faster than, say, state-of-the-art diffusion models like DiT-XL 2.
410 times. But that's not incremental. That's a different league.
It's a potential paradigm shift in efficiency, really rooted in just dramatically shortening that token sequence length.
Okay, before we dive into how they did this, let's quickly touch on the metrics. We'll be talking a lot about RFID and gFID.
Right, Reconstruction FID and generative FID. That's the Fréchet inception distance. It's basically measuring how similar the distribution of generated images is to the distribution of real images.
And critically for listeners, lower is always better for both RFID and gFID, right? Lower score means higher quality, closer to the real deal.
Precisely. So the paper aims to show low RFID, meaning TiTok compresses well without losing too much information, and low gFID, proving these super compact sequences are actually good enough to feed into generative models and get high-quality results.
Okay, let's unpack this, starting with the fundamental challenge TiTok addresses. Why move away from existing 2D tokenization in the first place? What's the limitation there?
Yeah, Section 1 really sets the stage. To understand TiTok's innovation, you have to look at the current landscape. Modern generative models, whether they're big transformers or diffusion models, they almost all rely on some kind of image tokenizer.
Usually VQGAN or maybe a VAE variant.
Exactly. And their job is crucial. Take that messy, high-dimensional pixel data, like a 256 by 256 by 3 image, and map it to a much smaller, more manageable latent space. Often, this latent space is structured like a 32 by 32 grid of tokens.
And that's the key point. The TiTok authors challenge that structured 2D grid in the latent space. That seems to be the bottleneck.
That's exactly their argument. The limitation is inherently tied to that static 2D grid structure. It's kind of the Achilles heel, especially if you're aiming for really aggressive compression.
Why is the grid the problem?
Because that fixed 2D grid enforces a very direct, very rigid mapping. Each token in the latent grid, say at position, ij, is forced to correspond directly to a specific patch of the input image, maybe an 8 by 8 or 16 by 16 block, at roughly the same spatial location.
So it locks the token to a physical region.
Right. And this spatial lock-in fundamentally limits the model's ability to efficiently exploit redundancies in the image. Think about a large area of blue sky or a uniform wall.
Yeah, a lot of similar patches.
Exactly. But the standard VQ model has to dedicate potentially dozens of separate tokens in that grid to represent those very similar patches. It's just not efficient. The model struggles to capture non-local similarities or represent large uniform regions in a shared abstract way.
So TiTok's goal is to break that rigid spatial correspondence. Where did they get the idea that this 2D structure might not even be necessary?
Well, they looked beyond the typical VQ autoencoder world and asked that key question. Is 2D structure necessary for image tokenization? And the inspiration seems to come from related fields, specifically high-level image understanding tasks.
Like classification or object detection.
Precisely. Or even multimodal models like CLIP or things like the perceiver resampler. These systems often work incredibly well using a fixed length 1D sequence of tokens, maybe just 64 or 128 tokens total.
And these tokens capture the high-level meaning, right? Like gats sitting on a mat.
Exactly. They encode the necessary semantic information for the task without needing a strict 2D spatial grid in their latent representation, and often without even needing a decoder to reconstruct the image.
But those systems aren't usually designed for pixel-perfect reconstruction. They capture the gist, not the texture.
That's the crucial difference and the challenge TiTok had to tackle. As the paper notes, these standard high-level 1D sequences, like what you might get from just passing an image through a VIT encoder, they tend to fail badly if you try to use them for high-fidelity reconstruction. They throw away too much low-level detail.
So TiTok needs the best of both worlds. The compression benefits and semantic richness of a 1D sequence, but also the ability to retain enough low-level detail for high-quality reconstruction and generation, all within that tiny 32-token budget.
That's the tightrope they have to walk. Which brings us neatly into Section 2. The actual TiTok architecture and the 1D tokenization method itself. How do they actually pull this off?
Let's get into the nuts and bolts. Architecturally, it sounds like it still builds on the VQ model foundation.
It does. At a high level, TiTok follows that familiar vector quantized model structure. You have an encoder, a vector quantizer, quant, and a decoder, deho.
And what specific components are they using for the encoder and decoder?
They opted for the vision transformer, or VIT, architecture for both the encoder and the decoder. They mentioned this choice was driven by its simplicity and its known effectiveness in handling long sequences and capturing global relationships, which turns out to be key here.
Okay, so VITs for the main blocks. Now let's walk through the 1D tokenization process step by step.
Right.
This is really the core innovation, especially how they get down to that small number of latent tokens, Kay.
Right. It starts conventionally enough. The input image dollar gets sliced up into patches, tiles. These patches are then typically flattened and projected into embeddings, standard VIT stuff so far.
Okay.
Now here's the crucial architectural tweak that makes TiTok different. These patch embeddings, TARs, are concatenated, joined together with additional special learnable tokens. Let's call them latent tokens, dollars. And dollar here is that target number, like KK3 number 2.
Ah, okay. So the sequence going into the encoder is actually longer than the final representation size. It includes all the normal image patches, plus these dollar special latent tokens.
Exactly. If you have a 256 by 256 image and use 16 by 16 patches, that's 256 patch tokens. So the input to the VIT encoder is actually 256 tokens long, so say 256 tokens plus 32 tokens, 288 tokens in total for that example.
Precisely. This combined sequence, let's call it MathBFP, a plus MathBFL, gets fed through the entire VIT encoder. The self-attention layers process all these tokens together, allowing information to flow between the image patches and these special latent tokens.
And the output of the encoder contains processed versions of all 288 of those tokens.
Yes, let's call the full output MathBFZ. It holds the encoded information for everything that went in.
Which leads us to the real trick, the step defined in equation 3. What happens next?
This is the absolute key. After the encoder does its work on the combined sequence, they simply discard all the output tokens corresponding to the original image patches.
They just throw them away.
Gone. They only keep the copy tokens that correspond to the initial dollar latent tokens. Yeah. These dollar tokens become the final 1D latent representation of the image, denoted MathBFZL. Wow, okay. So the VIT encoder's job is essentially to look at all the information spread across the hundreds of patch tokens and distill the most important essence down into just those dollar latent tokens.
That's exactly it. This deliberate discarding step is what achieves the crucial decoupling. The final latent representation size, capital dollar, is now completely independent of the image resolution or the number of patches. The power of the VIT's self-attention is forced to compress everything important into those few target tokens.
That breaks the direct link between input patch count and latent token count. The large VIT acts like a powerful information funnel.
A very efficient funnel. And once you have this compact 1D latent representation, a MathBFZD, which is still a sequence of continuous embedding vectors.
It needs to be quantized.
Right. It goes through a standard vector quantization step. Each of the dollar continuous embeddings, DFZFZ, is mapped to its nearest neighbor code vector from a learnable codebook, PUC$. This codebook has 9 entries, and for the main experiments, they used a fairly large codebook size, 1409667.
So now we have a sequence of dollar discrete token IDs, the compressed representation. How does the model get back to an image from just these, say, 32 abstract tokens,
Oh.
especially without that 2D grid to guide the placement?
This is where the decoder architecture and the inspiration from masked modeling like BERT or MAE come into play. It's quite clever.
Okay, how does the detokenization work?
The sequence of taller quantized latent tokens, let's call it MathBF Z1D, is fed into the VIT decoder, but it's not fed in alone. It's concatenated with another sequence of tokens, mask tokens.
Mask tokens, like the ones used in masked autoencoders.
Very similar concept. These mask tokens essentially act as placeholders for the spatial locations that the decoder needs to fill in. You create the sequence $and $i by taking a single learnable mask token embedding and just repeating it WF 4 times.
So you repeated exactly the number of times corresponding to the original image patches. For 256 by 256, or 16 by 16 patches, that's 256 mask tokens.
Exactly. So the input sequence to the VIT decoder is actually the $quantized latent tokens followed by these 256 mask tokens. For 300 TT2 tollers, that's 32 tollers, plus 256 equals 288 tokens, again going into the decoder.
So the decoder sees the compact semantic information, the 32 tokens, and the full spatial grid structure, the 256 mask tokens.
Precisely. The decoder's job, using its own self-attention layers, is to look at those 32 information-rich latent tokens and figure out how to use that information to predict the correct pixel values for each of the 256 mask token positions, effectively filling in the grid.
This is equation 4, right? MathBF these D1D on plus MathBF ND.
That's the one. The decoder has to learn how to distribute the conceptual information held in the 32 tokens across the spatial layout defined by the mask tokens to generate a coherent, detailed image MathBFM.
So a single latent token doesn't map to a single patch anymore. It potentially influences many output patches via the decoder's self-attention.
Exactly. Those 32 tokens are forced to represent more abstract concepts, things like smooth texture here, sharp edge along this boundary, or this region is mostly green. The decoder then uses these global concepts to reconstruct the low-level pixel details across the entire image grid represented by the mask tokens.
Here's where it gets really interesting then, because the self-attention of the decoder allows those few powerful latent tokens to communicate with all the mask tokens simultaneously. It breaks that strict locality.
Absolutely. A token isn't just reconstructing its local neighborhood. It's contributing based on the overall conceptual understanding encoded in the tokens. It's like the tokens hold the blueprint, and the decoder is the skilled constructor filling in the details everywhere based on that plan.
That non-local communication enabled by the VIT architecture seems critical for making this high compression work without just ending up with a blurry mess.
It's fundamental. It differentiates TiTok from simpler approaches that might just say use PCA or a shallow autoencoder. The depth and global reach of the VIT are key.
Okay, that covers the reconstruction part. Let's move to section 3. How do they use these compact TiTok tokens for actual image generation? They mention using the MaskGIT framework.
Right, so the tokenizer learns to compress and reconstruct. To show these tokens are actually useful for creating new images, they integrate TiTok into a downstream generative task using MaskGIT.
Why MaskGIT specifically?
MaskGIT is a good choice here because it uses a non-autoregressive bidirectional transformer for generation. Non-autoregressive is key for speed. It predicts multiple tokens at once, unlike autoregressive models that generate token by token, which is much slower.
And bidirectional means it considers context from both sides when predicting mask tokens.
Exactly. The overall pipeline is first you take your training images and pre-tokenize them into these compact 1D TiTok sequences, for example, 32 tokens each.
Using the already trained TiTok encoder and quantizer.
Correct. Then, during the training of the separate MaskGIT generator model, you randomly mask out some ratio of these 32 tokens. The generator's job is simply to learn to predict the original IDs of those masked tokens, given the unmasked ones.
So it learns the relationships and patterns within these ultra-compact sequences.
Precisely. And inference, or generating a new image, becomes an iterative process. You start with mostly masked tokens, the generator predicts some, you update the sequence, perhaps keeping the most confident predictions, mask again, and repeat for a few steps until you have a full sequence of 32 tokens.
Which you can then decode back into an image using the TiTok decoder.
Exactly. And this whole process is much faster than typical autoregressive generation.
And presumably even faster with TiTok because the sequence length is so short. Generating 32 tokens versus 256. That's a big difference for a transformer.
A huge difference. The computational cost of self-attention scales quadratically with sequence length. So reducing the lengths from, say, 256 down to 32 gives you a massive theoretical speedup in the generator itself. We'll see the numbers on that later.
Now, the paper mentions something important about training VQ models. They can be notably sensitive. How did they handle that? They introduced a two-stage training strategy.
Yes, this is a really practical and quite elegant solution to a common problem. Training VQ models, especially getting the balance right between the reconstruction loss, the code book loss, perceptual losses, adversarial losses, it can be tricky and require a lot of tuning.
So they developed a two-stage approach to make it more stable. Let's talk about stage one, the warm-up, using proxy codes.
The main goal of stage one is to stabilize the initial learning, particularly for the TiTok encoder and quantizer. Instead of immediately trying to make the model reconstruct raw RGB pixels, which involves complex losses like adversarial ones, they simplify the target.
Oh.
They use the discrete token outputs from an existing off-the-shelf pre-trained VQGAN model as the initial target. So they take an image, run it through the standard VQGAN encoder to get, say, 256 VQGAN tokens. These 256 tokens become the proxy target.
So the TiTok encoder quantizer isn't trying to predict pixels yet. It's trying to produce its 32 tokens such that
When those 32 TiTok tokens are somehow used, perhaps implicitly via the setup, to reconstruct the proxy 256 VQGAN tokens, the result is accurate. Or, perhaps more accurately, the TiTok model, encoder plus decoder, is trained to output an image that matches the image reconstructed from the proxy VQGAN codes using the VQGAN's decoder.
Let me rephrase that to be sure I understand. In stage one, TiTok, encoder plus quantizer plus decoder, is trained. Input is an image. The target is the reconstructed image produced by passing the proxy VQGAN codes, derived from the same input image, through the pre-trained VQGAN decoder.
Yes, that clarifies it. The target is the output of the proxy VQGAN decoder. This means the TiTok model only needs to learn the 1D tokenization and reconstruction process relative to a stable, high-quality target generated by a known good model. It essentially focuses the optimization purely on learning the effect of 1D compression, deferring the tricky pixel-level adversarial training.
It's like knowledge distillation, but focused on the intermediate representation and reconstruction quality, bypassing the unstable parts early on.
Exactly. It decouples learning the compression from learning the fine-grained pixel generation with GAN losses. It uses the proxy VQGAN's output as a high-quality, stable target signal.
And the paper shows this actually helps TiTok learn a better representation than the proxy VQGAN, not just mimic it.
Yes, the final results demonstrate TiTok ends up outperforming the VQGAN baseline, suggesting it learns a more efficient and effective compression even when bootstrapped this way.
Okay, so stage one stabilizes the encoder quantizer. What happens in stage two?
Stage two is the decoder fine-tuning stage. It's optional but generally beneficial for top quality. Here you freeze the weights of the now well-behaved TiTok encoder and quantizer.
So they're fixed.
Right. And then you only train the TiTok decoder. Now, the decoder is trained directly towards the actual pixel space, using the standard VQGAN training recipe, including the perceptual losses and the adversarial GAN loss.
So you introduce the complex pixel-level losses only after the core representation is stable.
Exactly. This significantly improves the final reconstruction quality, RFID, and makes the whole training process much more stable and easier to manage.
And the ablation studies really back this up, showing how crucial this two-stage approach is.
Absolutely. Table 3C in the paper gives a clear comparison. They tried training TiTok B64, base model, 64 tokens, using this two-stage proxy code method, and it achieved a really good RFID of 1.70.
Okay.
Then they tried training the same TiTok B64 architecture using a more traditional single-stage approach similar to the original Taming VQGAN paper, trying to learn everything at once with all the losses. The result, a much worse RFID of 5.15.
Wow, 1.70 versus 5.15. That's a huge difference.
It's dramatic. It really validates that the two-stage strategy using proxy codes for warm-up is highly effective for stabilizing training and achieving high quality, especially when pushing for these very compact latent spaces.
Okay, that makes the training process much clearer. Let's move into section 4, looking at the preliminary experimental insights that help them arrive at the final TiTok configurations. What did they learn from early tests?
These initial experiments were mostly done at 256 by 256 resolution, using a patch size of 16 and initially a smaller codebook size of 2024. They explored three main model sizes: TiTok S, small, around 22 M parameters; TiTok B, base 86M parameters, and TiTok-L, large 307M parameters.
And the first big insight, shown in Figure 4a, addresses the question right in the paper's title. Are 32 tokens actually enough?
Pretty much, yes. They tracked reconstruction performance, RFID, as they varied the number of latent tokens, dollars. Performance generally improved as dollars increased from 16 up to about 128.
But diminishing returns after that.
Exactly. The gains became marginal past $128. But the really critical finding was with the largest model, TiTok-L. With only 32 latent tokens, K3-1332, TiTok-L achieved an RFID of 6.6.
How does that compare to a standard baseline?
Well, they reference a baseline 2D VQGAN model, presumably using 256 tokens based on later tables, which achieved an RFID of 7.94. So TiTok-L with just 32 tokens actually outperformed the standard VQGAN using 256 tokens in terms of reconstruction fidelity.
Okay, so 32 tokens, handled correctly by a powerful enough model, can indeed be sufficient, even superior to less compressed standard methods.
That's the takeaway. It strongly suggests that 32 tokens can be a viable, highly effective, and extremely compact latent representation for images.
The second insight ties this compression directly to the size of the tokenizer model itself. Figure 4a also shows this, right?
Yes, it clearly shows a trade-off. If you want to achieve more compression, use fewer tokens part Ls without sacrificing performance, you need a larger tokenizer model.
The model capacity needs to increase to handle the extra compression work.
Precisely. The examples they give illustrate this. TiTok-B, the base model, using 64 tokens, achieved similar performance to the smaller TiTok-S model using 128 tokens.
Okay, so double the tokens needed for the smaller model to match.
Right. And similarly, the large TiTok-L model using just 32 tokens matched the performance of the medium TiTok-B model using 64 tokens.
So investing in more parameters for the ViT encoder allows it to more effectively capture and abstract the information, enabling higher compression ratios.
It validates the whole strategy. Use model capacity to absorb the redundancy and distill the image down to that minimal set of tokens.
Insight number 3 is fascinating, the idea that semantics actually emerge more strongly when you compress more. What's going on there?
This one is really interesting conceptually. They performed linear probing experiments, which is a common technique popularized by MAE and others, to assess the quality of learned representations.
How did that work? Yeah.
You take the frozen latent token embeddings produced by the TiTok encoder, and you train only a simple linear classifier on top of them to predict ImageNet class labels. The better the classifier performs, the more linearly separable and thus semantically meaningful the underlying representations are assumed to be.
Okay, so what did they find?
The results in Figure 4b were somewhat counterintuitive. They found that as the number of latent tokens decreased, going from, say, 256 down to just 16 tokens, the linear probing accuracy actually increased.
Wait, fewer tokens led to better classification accuracy from a linear probe? That seems backward.
It does seem backward initially, but think about why. When the model is forced into an extremely tight bottleneck, like only 16 or 32 tokens, it simply doesn't have the capacity to store lots of low-level redundant details, like the exact texture of every leaf on a tree.
It has to prioritize.
It has to prioritize capturing the most essential high-level semantic information. What is this object? Where is it located? What are the major structural components? It's forced to learn representations that capture the core meaning, which happens to be exactly what a linear classifier needs.
So compressing forces abstraction. It moves away from pixel patterns towards concepts.
Exactly. It acts less like a simple compression codec and more like a summarizer learning the conceptual essence. The peak linear probe accuracy for TiTok-L, 62.90%, was achieved at just K16 suckers tokens, strongly supporting this idea.
Which leads directly into the fourth insight.
Yeah.
These compact, semantically rich tokens are actually better for training the generative model downstream.
Yes. Figures 4c and 4a show this. Even the variants that had slightly worse reconstruction quality at very low K, like K3 $300 due compared to K 100-281, showed significantly better generative performance, lower gFID, when used to train the MaskGIT generator.
Why would that be?
It likely comes down to the input quality for the generator. A generative transformer probably finds it much easier to learn patterns and relationships from a sequence of 32 highly meaningful abstract tokens than from a sequence of 256 tokens where many might be encoding redundant local details.
A cleaner, more semantic input signal makes the generator's job easier.
Plausibly, yes. And the efficiency gains that come with this are substantial too.
Right, the speed aspect.
They quantify it clearly. Using K300-222 tokens instead of K25/656Cs resulted in a 12.8 times increase in the training throughput for the generator, measured in samples per second per GPU. It went from about 220 sample sec pu up to over 2,800.
That's just because the transformer has so much less work to do with the shorter sequence.
Exactly, that quadratic scaling bites hard with long sequences. And the sampling speed for generation also saw a big jump of 4.5 times speed up, going from roughly 28 sample sec pu to 123 sample sec pu.
Yeah, so faster training and faster inference, plus potentially better generative quality due to the semantic nature of the tokens. That's a compelling combination.
It really sets the stage for the main results.
Okay, let's get to those main results in Section 5. This is where they benchmark the optimized TiTok configurations against the state-of-the-art.
Right. For these main experiments, they focused on 3 key variants that seem to offer a good balance between model size and token count. TiTok S128, small model, 128 tokens. TiTok B64, base model, 64 tokens. And TiTok L32, large model, 32 tokens.
And they tested at both 256 by 256 and 512 by 512 resolutions. What patch sizes did they use here?
They used a patch size 516 nonces 6 for the 256 by 256 experiments, but switched to a larger patch size for 3 tutometers for the 512 by 512 experiments. This keeps the number of initial patches manageable, 256 patches in both cases, despite the higher resolution.
Makes sense. Let's start with the ImageNet 256 by 256 benchmarks, looking at Table 1 and Table 5 for the generator details. How did TiTok stack up on compression and reconstruction first?
The highly compressed TiTok L32 really shown here. It achieved an RFID, reconstruction FID, of 2.21. This is very competitive, basically matching the MaskGIT VQGAN baseline, which got 2.28 RFID.
But TiTok L32 did this using
Only 32 tokens compared to the 256 tokens used by the MaskGIT VQGAN baseline. That's 8 times fewer tokens for statistically equivalent reconstruction quality. It confirms the high compression doesn't necessarily hurt fidelity much.
Okay, now for the crucial test, generative quality, gFID. How did TiTok tokens perform when fed into the same MaskGIT generator architecture compared to using the standard VQGAN tokens?
This is where the benefit of the 1D semantic tokens really becomes apparent. Using the exact same MaskGIT VIT generator, switching the input from the baseline VQGAN tokens, which gave a gFID of 6.18, to the TiTok L32 tokens dramatically improved the gFID down to 2.77 with classifier-free guidance.
Wow, from 6.18 down to 2.77. That's a massive improvement in generated image quality just by changing the token representation.
It is. Even without using guidance, the improvement was substantial from 6.18 down to 3.15. It's strong evidence that these compact 1D tokens provide a much better starting point for the generative model.
How did this compare to diffusion models, which are often seen as the soda for quality, albeit slow?
They compared TiTok L32 against LDM4, a well-known latent diffusion model. TiTok L32 actually achieved a better gFID score, 2.77 versus 3.60 for LDM4.
Better quality and presumably faster.
Massively faster. TiTok L32 generated images at 101.6 samples per second, whereas LDM4 clocked in at only 0.4 samples per second. That's over 250 times faster generation.
So better FID score and 254x faster. That's impressive. Did they claim state-of-the-art at this resolution?
They did, with a slightly different configuration. Their best result came from TiTok S128, the small model using 128 tokens. With guidance, it achieved a gFID of 1.97.
And how does 1.97 compare to the diffusion soda?
It actually beats the reported gFID for DiT-XL2, a very strong diffusion model, which scored 2.27. So TiTok S128 gets a better FID score than DiT-XL2.
While still being faster.
While still being 13 times faster than DiT-XL2. So yes, they demonstrate state-of-the-art generative performance at 256 by 256, beating a top diffusion model on quality while maintaining a significant speed advantage.
Okay, that's compelling at 256. What happens when they scale up to 512 resolution? This is where diffusion models really shine, but also where token counts for VQ methods usually explode.
Right. The standard MaskGIT baseline at 512 by 512 requires 124 tokens using its VQGAN tokenizer. That's a very long sequence for the generator.
How did TiTok compare in terms of token count?
Their efficient TiTok L64 variant, large model, 64 tokens, needed only 64 tokens for the entire 512 by 512 image. That's 16 times fewer tokens than the 1024 required by the baseline.
16 times shorter sequence. That must lead to incredible speedups.
It does. This is where we see that headline 410x speedup number. Looking at Table 2 and Table 6, TiTok L64 achieve a gFID of 2.74 with guidance. This again beats the DiT-XL2 diffusion model, which scored 3.04 gFID at this resolution.
Better quality than DiT-XL2.
And generated samples at 41.0 samples per second compared to DiT-XL2's incredibly slow 0.1 samples per second. That's where the 410x faster figure comes from.
41 samples per second versus 0.1. That's the difference between near real-time generation and waiting minutes per image.
It's a game changer for practical deployment if you need high-resolution generation at scale.
Is that TiTok L64 the absolute best performing variant at 512 by 512? Or did another one edge it out on pure quality?
The variant that achieved the absolute lowest gFID score best quality at 512 by 512 was TiTok B128, base model under 28 tokens. It reached a gFID of 2.13.
How does 2.13 compare to DiT-XL2's 3.04?
It's substantially better. So TiTok B128 significantly outperforms DiT-XL2 on quality, while still being much faster, generating samples 74 times faster than DIT.
So even their highest quality variant maintains a very large speed advantage over diffusion.
Definitely. It reinforces the core trade-off. You can push TiTok for extreme speed, like L64, or tune it for SOTA quality, like B128. And in both cases, it seems to offer significant advantages over strong diffusion baselines, at least on the FID metric.
There was also that interesting side note in Table 6 about classifier-free guidance and how the compact models responded to it. Can you elaborate on that?
Yes, that's quite revealing. They noticed that the very compact variants, particularly TiTok L64, performed remarkably well even without using classifier-free guidance. Its gFID without guidance was 3.64, which absolutely crushed the baseline MaskGIT's 7.32 without guidance.
So the raw tokens themselves lead to much better generation quality compared to the baseline.
Exactly. But here's the interesting part. While adding guidance did improve TiTok L64's score down to 2.74, the relative improvement was less than what you typically see for other models or even for the less compressed TiTok variants.
Why would a model benefit less from guidance? Isn't guidance supposed to always help?
It might tie back to that emergence of semantics idea we discussed earlier. If the 32 or 64 tokens are already highly constrained and forced to encode clear semantic information, there might be less ambiguity or noise for the guidance signal to clean up.
The input sequence is already semantically pure, so to speak.
That's the hypothesis. Guidance often works by pushing the generation away from unconditional noise towards class-conditional concepts. If the tokens themselves are already strongly conceptual, guidance might offer diminishing returns.
Which it suggests.
It suggests that maybe the standard inference techniques like classifier-free guidance, which were developed for models using more redundant representations, might not be perfectly optimal for these ultra-compact 1D sequences. There could be potential for developing new inference or sampling methods specifically tailored to leverage the properties of these dense semantic TiTok representations even further.
Fascinating. Okay, to really cement our understanding, let's quickly cover the key ablation studies in Section 6. They ran some tests to isolate why TiTok works. What was the first critical ablation?
The first one, in Table 3C, directly tested the necessity of the proposed 1D tokenization approach versus just using a compact 2D grid.
How did they test that?
They took their TiTok B64 model, base size target 64 tokens, and compared the standard 1D version, using the 64 special latent tokens law dollars, against a modified 2D variant. In this 2D variant, they removed a latent tokens dollar and instead tried to directly use a representation based on the image patches themselves, but still constrained to somehow represent the image with only 64 units while maintaining the 2D structure. It essentially forces the model back into the VQGAN style fixed 2D correspondence, just with way fewer tokens.
Okay, so comparing 1D TiTok B64 versus a 2D constrained version with 64 units, what happened?
The results were stark. The standard 1D TiTok B64 achieved an RFID of 5.55. This was in the single-stage training setting, for fair comparison here. The 2D constrained variant performed terribly, getting an RFID of 15.58.
Much worse.
Catastrophically worse. This result is crucial because it demonstrates that if you simply try to apply extreme compression, like 64 tokens for a 256 by 256 image, while sticking to the rigid 2D grid structure, the model fails to produce reasonable reconstructions. The flexibility of the 1D approach, allowing tokens to represent global concepts non-locally, is validated as essential for achieving high compression ratios effectively.
It directly proves the limitation of the fixed 2D grid under severe compression. Okay, what was the second main ablation? It had to do with masking schedules for the generator training.
Right. Ablation 2 in Table 3b looked at how different masking schedules affected the generative performance, gFID, when training the MaskGIT generator with TiTok tokens, specifically the highly compact TiTok L32 tokens.
What are masking schedules again?
They determine the ratio of tokens that are masked at each step of the iterative generation process. MaskGIT traditionally works well with a cosine schedule.
But TikTok preferred something different.
Yes. When using the TiTok L32 tokens, they found that the ARCO schedule, giving 4.94 gFID, or the linear schedule, 4.95 gFID, actually performs slightly better than the standard cosine schedule, which got 5.17 gFID.
Why would the best schedule change?
The interpretation offered in the paper links back once again to the semantic nature of the TiTok tokens. Cosine schedules tend to mask a higher percentage of tokens in the early generation steps. This works well for standard image tokens, which have high spatial redundancy, similar to how masked autoencoders like MAE use very high masking ratios, for example, 75% for images.
Okay.
But the TiTok L32 tokens are thought to be much more compact and semantically dense, perhaps more like language tokens. Language models like BERT typically use much lower masking ratios, around 15%. The linear and ARCO schedules tend to use lower masking ratios in the early steps compared to cosine.
So because the TiTok tokens are already information-rich, masking too many of them early on might actually hurt performance, making schedules with gentler initial masking preferable.
That's the reasoning provided. It suggests the optimal way to generate from these tokens might be closer to language generation strategies than traditional image patch generation strategies.
Interesting connection. Finally, let's just touch on the implementation details and resource usage mentioned in the supplementary materials. It's always good to know what it took to run these experiments.
They were quite transparent about this. For the flagship TiTok L32 variant, large model, 32 tokens, training the tokenizer, the encoder, quantizer, decoder, required a substantial cluster. 64 NVIDIA A100 GPUs, the 40 GB version, running for about 74 hours.
Okay, that's a significant but not astronomical amount of compute for training a large foundation model component these days. What about training the generator?
The generator training was much faster, thanks to the short 32 token sequence length. That only required 32 A100 GPUs for about 12 hours.
So the main cost is upfront in training the powerful tokenizer, but the downstream generator training is relatively efficient.
That seems to be the case. They also confirmed details for the final models, like using the larger codebook size 140961s, training the tokenizer for 200 epochs, and performing that crucial decoder fine-tuning stage 2, for around 500,000 iterations.
And they confirmed the use of guidance for the benchmark results.
Yes, they explicitly state that the results reported W guidance used classifier-free guidance, and they even provide the specific guidance scales and temperatures used for different variants and resolutions. For example, scale 4.5, temp 9.5 for TiTok L32 at 256 by 256. This confirms the results were achieved using standard, albeit tuned, inference techniques.
Good to know. That thoroughness adds confidence. Okay, that covers the core technical details and results. Let's try to synthesize this for our listeners. What's the main takeaway from this deep dive into TikTok?
I think the primary achievement is demonstrating a fundamental shift in how we can think about image representation. TiTok successfully broke free from the rigid 2D latent grid that has dominated VQ-based methods.
Moving to that flexible 1D sequence using vision transformers.
Exactly. And leveraging the power of VITs allowed for really unprecedented information compression. This transition delivered two major wins, empirically demonstrated. First, a drastic reduction in the number of tokens needed to represent an image by up to 64 times.
While maintaining quality.
Right. And second, this compression enabled state-of-the-art generative performance, particularly in terms of speed, achieving up to 410 times faster inference than leading diffusion models on benchmarks. It really validates their core hypothesis. Maybe that explicit 2D structure isn't necessary for highly effective image tokenization?
The results within the VQ MaskGIT setup seem incredibly strong.
They are. And that brings us to the concluding thoughts, which often stem from the paper's own limitations or future work sections. TiTok was validated using the specific setup VQ quantization, MaskGIT generation, largely because it provided a stable and comparable framework.
But the core idea, the 1D tokenization, isn't necessarily tied only to VQ or MaskGIT, is it?
Not at all, theoretically. The authors themselves suggest this. The core concept of using a VQGAN encoder to distill patch information into a small set of latent tokens, discarding the patch tokens, and then using those dollar tokens with mask tokens for reconstruction or generation. That's a generalizable architectural pattern.
So what are the implications? Where could this go next?
Well, you could imagine applying this 1D tokenization idea to other formulations, maybe a 1D VAE instead of a 1D VQVAE. Or, perhaps more excitingly, could you integrate these ultra-compact 1D TiTok sequences into other generative frameworks, like diffusion models?
Using TiTok as the highly efficient encoder-decoder for a latent diffusion model.
Potentially. If you could train a diffusion model directly on these 32 semantic tokens instead of a much larger, less structured latent space, you might get the quality benefits of diffusion with some of the speed benefits of the short sequence. That's an open research question, of course.
And beyond images, the paper hints at other modalities.
That's perhaps the most provocative thought to leave you with. If forcing representation into a tight 1D bottleneck works so well for images by compelling semantic abstraction, what about data with even more redundancy, like video?
Instead of processing video as sequences of 2D grids, maybe treat it as one long, dense 1D sequence of TiTok-style semantic tokens.
Exactly. Could you represent entire video clips or maybe even 3D scenes or other complex data structures using highly compressed 1D sequences? If this approach scales, it could unlock dramatically more efficient ways to model and generate complex high-dimensional data far beyond static images.
The potential to apply this core idea, extreme compression via 1D semantic distillation, using transformers to unlock efficiency in video, 3D, or other domains, seems like a really critical and promising direction for future work.
Absolutely. The success of TiTok in the image domain really opens the door and accelerates the search for these kinds of efficient, unified 1D representations across many different types of data.
An image is worth 32 tokens. A powerful idea with potentially far-reaching consequences. Thank you so much for joining us for this very detailed technical deep dive into the TiTok paper.
And thank you for sticking with us as we unpack the methodology, results, and implications presented in this fascinating work.